You've seen it 1,000 times. You tear open a new pair of shoes, unbox a brand new guitar, crack open a bottle of vitamins, and there it is, that small, mysterious little packet staring back at you with 4 words that somehow make it infinitely more tempting. Do not eat. But why? What's actually inside? And what would really happen if you just ate it? Today, we're going deep into the science of one of the world's most misunderstood materials, silica gel, because the truth is stranger, more fascinating, and honestly way more anticlimactic than you'd expect. Here's the wild part. Silica gel isn't some exotic synthetic chemical cooked up in a lab. It starts as something you've stepped on your entire life: sand. Silica, also known as silicon dioxide, is one of the most abundant materials on Earth. It makes up the majority of the planet's crust, and yes, it's the same stuff you find at the beach, but turning plain old sand into those tiny miracle beads is a surprisingly precise process. First, the raw silica sand is mined, washed, dried, and sifted until every grain is perfectly uniform. Then it gets mixed with sodium carbonate, blasted with heat, and combined with an acid. And here's where the magic happens. That acid triggers a reaction that links all the silica particles together into a jelly-like matrix. Picture it like constructing a microscopic sponge, molecule by molecule. That sponge structure gets washed, dried, and hardened into those small, glassy little beads we all recognize. On a molecular level, they're chemically identical to beach sand. The only difference is the structure hiding inside. This is where things get genuinely mind-blowing. Inside each silica gel bead is a labyrinth, an enormous, microscopic network of tunnels and chambers. And we mean enormous by microscopic standards. 1 single gram of silica gel contains over 700 square meters of surface area. That's roughly the size of 3 tennis courts, packed into something smaller than a sugar grain. But this tunnel network isn't just impressive architecture. It's a trap, specifically designed to catch water. Here's the science. The silicon dioxide molecules inside silica are held together by what chemists call polar covalent bonds. Without getting too deep into chemistry class, these bonds create a kind of natural attraction to other polar substances, and water is one of the most polar molecules in existence. So when you drop a silica gel packet into a humid environment, it basically becomes a magnet for moisture. Water molecules in the air are pulled toward the bead's surface, and then, through a process called capillary condensation, sucked deep inside through those microscopic tunnels. The result? Each bead can hold up to 40% of its own weight in water. A standard 5-gram packet can soak up around 2 grams of liquid. And here's the creepy part. Even when a bead is completely full of water, it doesn't feel wet. All that moisture is locked away inside the internal network, invisible to the touch. Water isn't the only thing silica gel traps. Those same polar bonds also attract ammonia, sulfur dioxide, and several other gases, which is why you'll find silica-based materials inside gas masks and industrial filtration systems. It's not just keeping your sneakers fresh, it's potentially saving lives. Now, silica gel isn't infinitely patient. In a super humid, sealed space, a packet can hit full saturation in as little as 1 to 2 days. In a more moderate environment, it might last a week. But here's something most people don't know. Silica gel never really dies. Toss it in a hot oven, bake out the trapped moisture, and it resets. Good as new. Functionally, these little packets can last forever. We've been mass-producing silica gel commercially since 1919, and over a century later, it's everywhere because it works. At home, it keeps your chips crispy, stops your vitamins from clumping, and quietly absorbs the aromas from your cat's litter box. In museums, conservators pack silica gel into display cases to stop metal artifacts from rusting and taxidermied animals from growing mold. Hospitals use it to keep surgical equipment sterile during storage. And then there's space. NASA uses a special ultra-lightweight form of silica gel called aerogel, sometimes called frozen smoke because it's nearly transparent and impossibly light, to insulate Mars rovers from temperature swings that can hit -80 degrees Celsius. Aerogel was also used on the Stardust mission to literally catch comet dust traveling at over 20,000 kilometers per hour without destroying it. The same material keeping your jerky fresh is also collecting samples from the edge of the solar system. You've been patient. Here's the moment of truth. You eat a silica gel packet. What happens? Honestly, not much. Those do not eat labels are there primarily because the packet is a choking hazard, not because silica gel is some deadly poison. Your body is mostly water, and even if that packet absorbed its full 2 grams, you'd replace that and more with a single sip of water. More importantly, silica is chemically inert, meaning your body cannot metabolize it, break it down, or convert it into anything toxic. It basically just passes through. That said, eating a large quantity would be genuinely unpleasant. All that moisture-wicking power could dry out and irritate the mucous membranes lining your digestive tract, causing stomach pain and diarrhea. Not exactly a fun afternoon. There is one real warning worth taking seriously. Some silica gel beads are coated with cobalt chloride, a compound that changes color to indicate saturation levels, blue when dry, pink when full. Cobalt chloride is actually toxic and potentially carcinogenic. If you see colored beads in a packet, that's your cue to keep that far away from food, pets, and children. But for plain, standard silica gel, eating a packet is less medical emergency and more uncomfortable mistake. The next time you pull a silica gel packet out of your shoebox, take a second to appreciate what you're holding. It's a material born from beach sand, engineered at a microscopic level to trap invisible molecules out of thin air, capable of preserving everything from ancient museum artifacts to Mars rover electronics. And it's been doing it quietly, invisibly, for over 100 years. And no, you still shouldn't eat it. But at least now you know why.